Recording is rolling. It is Monday, April 13th. Gonna do fluid mechanics review with you guys. Guys, this is the last topic by AP book. Right, we're gonna focus on these equations down here. Guys, it's the last set of equations. Go to your PowerPoint slides today and also come up with some challenge questions for you guys. Okay, so I wanted to get to this, but we're gonna have to do this tomorrow. All right, tomorrow. Okay. You guys remember back on Friday? I sent you guys here. Let me show it to you guys. I'm gonna point it out here on AP Classroom. I opened up an assignment a few days ago. It's this one right here. You guys see Unit 7 and Unit 8. There's 10 questions. It was 5 of each, so 5 and 5. Right. So, looks like a lot of you guys have done this. Right. So if you haven't done this yet, which is some of you guys, then finish this tonight, and then tomorrow I wanted to go over those with you guys. Okay? You guys see that? Okay. Oh, next thing on the list is actually this one right here. You guys see practice exam 2, multiple choice question? Now, their AP offers 3 practice exams. We already did one a few weeks ago. And remember, these practice exams have 2 halves to them. There's a multiple choice half and there's a free response question half. So here's how we're going to do practice exam 2. The multiple choice questions I'm going to let you guys do for homework. And I'll give you guys about a week. So if you have these done by next Monday, then that should be enough time. So I can eventually debrief these with you guys. Now, the free response packet, I want to... I actually have these printed out. I have the free response question packet printed out. And I want to give this to you guys in class on Wednesday and Thursday. Guys, how long do you have? How long do you have to complete all 4 FRQs on the real exam?
An hour.
Oh, 90 minutes. Should be 90 minutes. Right. So 2 class periods is almost exactly 90 minutes, right? Once you subtract out the time for attendance and all that stuff, right? It's pretty close. So almost exactly 2 class periods. So it'll give you a good idea how much time. But if you want to time yourself on multiple choice questions, that's also 90 minutes there. That might be a good idea. You guys, could you do this? Could you do like half an hour Monday homework, half an hour Tuesday homework, half an hour Wednesday homework, and then boom, you finish them off? Okay. No, represent the amount of time also. All right. So you guys got that written in your planner to do the AP Classroom, practice exam 2, multiple choice. You guys got about a week to do that. There. All right. Let's go over to fluid mechanics. So guys, what's that Greek letter right there? Rho. Greek letter rho stands for density. Guys, density is a ratio of whatever what. Yeah, mass compared to volume. Okay. Right. So if I have a container of water and I double the amount of water, guys, if I double the amount of water, what happens to the density of water? Huh? Guys. Right. If I double the amount of water, what happens to the density of water? Yeah, stays the same. Right? Now I could say I double the mass and I double the volume, but the density, because density is an intrinsic property. In fact, you guys might know a number. Guys, what is the density of water? 1 gram per cubic centimeter, or 1,000 kilogram per cubic meter. Yeah. So in this class, we might tend to use 1,000 kilogram per cubic meter for SI units. Oh, you can do this experiment. You can take this 10 Newton weight right here. You guys see this weight is 10 newtons, 10 newtons weight. Right? And then submerge this in water. Ooh, now I see 3 forces. Earth is pulling it down. The tension force decreased to 7 newtons. And there's also this buoyant force. And it turns out that buoyant force is exactly equivalent to the weight of water displaced. That's what I'm trying to show with this picture here. I think I showed you guys Paul Hewitt actually did this experiment. All right, you guys saw it? All right, so weighted fluid displaced, which you can further break down like that. Okay? All right, so you guys go with buoyant force? It's also, Archimedes principle. Do you guys remember this box lab you guys did? All right, so you guys were trying to fold a optimal box, maximum size box from choosing some optimal X. Okay. Right here, let's flip over, give you guys a challenge question over here. Suppose you have a boat. And it's right here. Right. And let's say this boat weighs 1,000 newtons.
Oh, the big boat.
1,000 newton boat.
Not really.
Guys, what's the buoyant force holding up the boat?
That was like
Yeah, also 1,000 newtons. Okay. What if you could do this? Guys, what if you could freeze time? Okay, you guys see it? I'm going to freeze time. I'm going to take the boat out of the water. And now is there a void in the water? Do you guys see that? Guys, follow the story with me. Okay. So I just froze time. I pulled the boat out of the water. Now there's a void there, and I'm gonna fill that void with water. And I just hashed it in pink ink. Okay. Guys, what if I weighed that water? How much would that water weigh?
500 miles. Yes.
Oh, okay, yeah, 100 kilograms mass or 1,000 newtons of weight. Yeah, that's true. Okay, it's all the same. Okay. Now, how about this? Let's do a new scenario. You guys remember Pete the Pirate? Let's say this is Pete the Pirate's rowboat. And he fills his boat with treasure. Oh, look at all that treasure. Ooh, treasure. Treasure. Arr. And let's say this boat now weighs 2,000 newtons, including the treasure.
Wait, how many kilos is food?
What's the buoyant force holding up the boat plus the treasure? 2,000 newtons. Okay. Guys, if you compare these two scenarios, old scenario compared to new scenario, okay? How much water am I displacing now compared to before? Yeah, double the amount of water, double the volume of water, because I know the buoyant force is rho water GV. Okay? The gravity field's the same for both of these. The density of water is the same. That's the same. That's the same. So if the buoyant force is doubled, then the volume displacement must also be doubled. All right. So then, okay, you guys did all this. All right. There's the dimension constraints, and here's the potential buoyant forces based on the volume of the boat. Okay, you guys did all that. All right, guys, two slightly different formulas, and these are both on your AP formulas page, exactly where I pointed them out in the bottom right. Guys, pressure versus buoyant force. Here, guys, here we look up here. So, of course, you can chop them straight off the page anyway, but I think it is better if you know these, because you'll maybe intuit them better, understand better, be able to access them faster. What is pressure equal to? What?
Is there a certain force over energy?
Yeah, okay, so from this point of view, yeah, I'm looking for density of the water, gravity field, and how deep you dive into the water. Call it H for depth. Okay? Versus buoyant force is equal to what? It's a very similar formula, but a little bit different. How's this one go? You guys write that in your notes. Yeah, instead of an H for depth, now you have V for displaced volume. Okay, that's the only difference. How about this? Guys, everybody look up here. Focus here. I got a question for you guys. Suppose you dive down 10 meters in the water. You guys see you're 10 meters deep? Ooh. Do you guys feel some pressure? Right. Now let's triple that to 30 meters. Now you're 30 meters deep. That's 3 times the depth. Guys, if you go 3 times deep, what just happened to the pressure on you? 3 times the amount. Okay, and actually, this form is actually what's called gauge pressure. So it's not including the atmosphere pushing above, right? But you could also add that on later. Okay? But let's say we're just looking at gauge pressure due to the water. Yeah, 3 times as deep would be 3 times the pressure, 3 times the gauge pressure, I should say. Okay. Okay. How about this, guys? Oh. So we're back to 10 meters deep, and now you're going to dive down to 3 times. Now you're 30 meters deep. So you went from 10 down to 30 meters. Guys, what has happened to the buoyant force on you?
The same.
Guys, it's the same buoyant force. Because the density of water is about the same. Your volume is about the same. Gravity field is about the same. Yeah, guys, everything's the same. Okay. So, guys, does buoyant force depend on how deep you are? No, not much. You're completely submerged. Now, this iceberg looks like it's floating a little bit, so that's a little different. Right? But as long as you're completely submerged, it doesn't matter really how deep you are for buoyant force. But the pressure is different. Right? But the pressure differential, that could be the same from bottom of you to the top of you. That's why the buoyant force can be the same. All right, you guys good with pressure versus force for water? All right. Here's a question that you'll almost certainly see, or some variation of this. Is what if you have a floating iceberg, or it could be a floating boat, or it could be a floating cube, or something like that. Now, guys, if it's just floating there at rest, is that equilibrium? As soon as you think in terms of equilibrium, can I write that right there? Sum of forces goes to 0. Okay. And I see 2 forces, so those have to balance out. Okay. Now, one way you could go with this question, how I'm directing this is, what's the percent volume displaced? You guys see the part that's submerged compared to the entire iceberg? Okay. Do you guys remember how this finishes off? Here, go ahead. Let me pause that slide right there. You guys all have your notebooks out. So, finish the rest of that fruit. Get get to that very end goal right there. What's the percent submerged in terms of any relevant variables? Do you guys think? Use your imaginations here a little bit.
What team?
No.
It ends up being in.
No.
Hmm.
I found it with my.
It's being what? Yeah, guys. What is the buoyant force formula? Yeah, rho VG. Okay, so density of the surrounding fluid or water in this case, the volume displaced and gravity field, that could all go into buoyant force. Alright, so you see from the free body diagram, there's one up force, one down force, so it's have to zero out. Okay, we got that. Okay. Now, guys, what did you just substitute for buoyant force? Rho VG. And when I say rho, which rho? Is it rho of the ice or rho of the water? Rho of the water, because it's surrounding fluid. Okay. And oh, you know what? You can actually make a similar substitution here. Guys, what is the mass of an object in terms of its density? Density times volume. Yeah. Because if you have some density, you multiply it by the volume. Doesn't that just bring you back to this math here? Yeah. So we did. But guys, what this would be the density of ice, right? And which volume would this be? Would it be the submerged volume or the entire volume of the iceberg? Yeah, the entire iceberg. Yeah. Okay. Okay, so we got that. Okay. So at some point we're gonna get this. Is that okay? Right. Now, ooh, what variable cancels out? Ask this a different way. Okay, suppose you took this whole system up to the moon and you somehow had a pool of water on the moon. Would this iceberg float higher, lower, or the same on the moon? The same. How'd you know?
Water.
Because gravity cancels out. You see gravity field can cancel out? Now you need some gravity to make this work, but after that, it doesn't matter how much. The magnitude of that gravity field cancels out. Right? You guys got that? Okay. And then you rearrange the other variables, and what's the final answer? This is what goes right here. Density, ice over water. There you go. So, for example, if something's floating, guys, if this iceberg is floating, what's more dense, the ice or the water? The water has to be more dense, and the ice has to be less than it. Okay. Okay. So this displacement volume compared to the entire volume, that might be something like 0.9, for example. Okay. And then, the ratio of these densities could also reasonably be about 0.9. You guys see that? Same thing? Okay, so look for some version of that on the AP exam. I don't know exactly how they're going to ask it, but I bet you're going to get some cube floating and something. Ooh, Pascal's principle, and this picture here, I'm looking at a hydraulic lift. Okay, so like how much input force does it take on the left side to lift this car here? And so the principle here is that pressure in this hydraulic fluid is undiminished. So the pressure on the left side and the pressure on the right side are the same. So it's the same pressure. Right? There's only one pressure inside that fluid, pretty much. Okay. And guys, what is pressure? It's what over what?
Force over area.
Yeah, force compared to area, force over area. Okay, so the left side force is your input force. You're pushing down on this piston. And it's a very small cross-sectional area piston, which is at A1. And then the car is a large cross-sectional area, but also a large force. All right, is that okay? That's it up? All right, so let's switch over and have you guys solve one of these. You guys ready to solve one of these? You guys ready for me to switch to the screen? Right here. Give you guys a moment to jot that down. Pascal's principle. All right, let's get a picture going here. Picture time. All right, so go ahead, draw a hydraulic lift. So you got a small piston and a large piston. Okay, let's spell this all with hydraulic fluid. Okay, here, maybe I'll just hatch this in pink ink. Okay, so everything I'm hatching in pink ink is some hydraulic fluid. That's okay, hydraulic fluid. And let's put a car on the side.
It's a weird thing.
I'll tell you guys the weight of the car. MG car.
Don't worry, they'll come to you.
Let's call it 10,000 newtons. 10,000 newton car. Okay. Which means it has to be held up by the same force. Call it normal force. Okay. Now I wonder what input force. I'll call it F input here. To be able to lift the car. This car is not sitting on a giant piston. Here's another piston over here. Right. You guys get the premise so far? Right. Now you can't solve this yet because I haven't given you enough information. Because what information? Here, maybe you want to make something like this. Think a little bit. what information do I still have to give you?
The area.
Yeah, so something about how big are these pistons related to each other. So it's gonna be a little tricky. See who catches this. Let's say this left diameter is 1 meter exactly. Let's say its right diameter, called D1 and D2, is like 3 meters. Okay. You guys got those two diameters? Okay. Go ahead. Solve what input force do you need to lift that car? So I'm giving you guys a head start here. Giving everybody a head start. Go ahead and solve that.
Did you already have one?
You saw the PowerPoint course how to set this up.
Yeah, I can.
You're reading a new one?
What input force do you need?
Yeah, I actually did.
Okay, so as soon as somebody gets it, raise your hand. Ethan, what'd you get? Oh, let's check something.
So what is the height?
Okay, so does that height of the fluid matter so much? Not significantly. Yeah, we're gonna ignore the height differences. Wait, nobody said the number I'm looking for yet.
Wait.
Is it 1,800?
Not quite. I throw a little curveball in the middle. Because I asked you guys what other information do you need? You said, oh, well, you need the areas of the pistons. Ah, Ryan got it. Ryan got it. Yeah. Yeah. Okay. Because the answer is about 1,100 newtons of force. Okay. So let's take it away. Okay. Now, you guys said, well, you need the cross-sectional areas, which is true, but that's not exactly what I gave you. Guys, and AP could totally do this. I've seen AP do this. That's why I'm doing it here. Okay, did I give you cross-sectional areas? I need the diameters. Oh. Could you imagine if you're looking from above, these could be circle shapes? Let's call them circles. Okay. Guys, how do you find, guys. Right, here, raise your hand if you know this. Right, hopefully this will be in most of the class. What is the area of a circle based on its diameter? Guys, everybody, raise your hand if you think you know the answer. Okay. All right. Who wants to volunteer? All right. What you got?
5 times diameter over 2 squared. So like
Okay.
diameter over 4 pi.
Yeah. So you said pi times and then d over 2 squared. Yeah. So you can do this. You can do this. The same thing. Yeah. Oftentimes pipes are listed by their diameter. So if you have a 3-inch pipe, they're talking about the diameter of the pipe. Okay. So it's good to know this. Right? Think about circular cross-sectional area. Okay. Now, what we're saying here is that the pressure on the left side, which is force over area, is equal to the pressure on the right side, which is a different force over a different area, but it's the same pressure. Okay, straight from the PowerPoint. Okay. Now, here's your F input, which we're solving for. This cross-sectional area, I'm going to list as pi over 4, and this diameter of 1 meter being squared. And then on the right side, I got 10,000 newtons of force acting on pi over 4, 3 meters being squared. Okay. So I left the pi over 4 in the equation. I didn't solve for the actual areas numerically because there's something else I want you guys to see. Guys, look up here. All right, I really want everybody to see this. What cancels out left and right? Yeah, the pi over 4 bit. Right. And what that means is this. Remember how I was saying these could be circular cross-sectional areas? What if I did this? What if I changed it to like square cross-sectional areas or like pentagons or something weird? Would it, as long as I knew the proportions, would it make any difference or would it just be the same at this point? The same. Because pi over 4 just makes it a circle. But it doesn't matter what shape because it cancels out anyway. Okay. So now we got this. So 1 squared is 1. Guys, what's 3 squared? 9. So it'll be 10,000 divided by 9. So you should get F input. I think it's like 1111 newtons. Yeah, so AP would probably round that to 2 significant figures and just call that 1100 newtons. Okay. And so that's the input force, and that'll lift the car. Pascal's principle. Alright. And then some of you guys are still getting out your notes. Okay, so do the formula check here. We got densities mapped per volume. Here we go. Here's pressure squared per area. We just use that. I'm pointing out formulas. Here's gauge pressure is rho gh, but right above that they do absolute pressure. So if you had some rho gh like inside a pool water, and then you add the atmosphere on top of that, you get the absolute pressure of that. So we got Archimedes right here, point force is rho GD. We've got and then these last two we haven't quite hit yet, but this is conservation of flow and Bernoulli, which we're about to do. All right, you guys ready to go back to the PowerPoint? You guys ready? What you need there? All right, back over here. All right, so you guys can solve hydraulic lift. Right, hydraulic lift. So when you almost certainly see this on the AP exam. Oh, okay. So there we go. There's that. There's that. Boom, boom. Oh, YouTube. So, no, this one I have both ends are open to the atmosphere. That's usually the case. Doesn't have to be. Oh, guys, what can you say? Guys, focus here. Look up here. What can you say about the pressure right here versus the pressure right here? It's the same pressure. Is this pressure equal to this pressure? Yeah. Okay. But there's a different story how you get there, the left arm and the right arm. So, here, let's switch over here back to your notes. Set you guys up at YouTube. We're gonna solve something here. So in your notes, draw YouTube. Let's have each end open to the atmosphere. So I'll say open to atmosphere. That's that side and also that side. Right, we'll just keep both ends open. So the atmosphere is pushing pretty much the same, left side, right side. Right, so let's throw some fluids in here.
It's always like.
Or you can see it. If I were you, I would have used fibers.
The biggest thing is.
Right. Now, there's different ways you can be given these heights. So I'll just make up something like this. How about? Alright, let's call this. How about 10 centimeters? We'll call this 15 centimeters. And let's call this another 10 centimeters. How about that? Okay. And let's do some mystery fluid here. And let's call this water. So here's your water. Maybe I'll just call this oil. How about that? So we have some pink oil. We have blue water and pink oil. You guys need some blue water and some pink oil?
How do you feel about that?
Now, I think you guys told me earlier today. You guys know the density of water is, of course, what?
1 kilogram per.
Yeah, 1,000 kilogram per cubic meter. Right, so you guys know that. Right, so you guys know that, right? Question. What is the density of the oil? Density of the oil. Go ahead, solve for the density of the oil. Right, when somebody gets it, raise your hand.
Like
James Salt, I think that's right. Yeah, that's right.
I'm so like.
99,000 newtons.
It's gonna be in kilogram per cubic meter, right?
They're not newtons. That's it. 147 kilograms per cubic meter. That's what Chase has. That's the Chase.
Alright, somebody find what is the density of that pink oil?
Like if I need something, I know how.
Who's gonna get it first? Density. Okay, so on the left side, I got 15 centimeters. On the right side, that's 10 centimeters and then 10 centimeters, so 10 to 10. And the density of water is 1,000 kilogram per cubic meter. Exactly. So what's the density of that pink oil?
And she also doesn't work.
Yeah.
But
No, she's 100% not.
Yeah, all right, Felipe got it. 500 kilogram per cubic meter. All right, Felipe, winner. Ding, ding, ding. And so there's a couple of different ways to set this up. I'll show you guys what I would do. Guys, I would just go to this line right here. I'm gonna take this as height 0. You guys see that? And I'm gonna, guys, is the pressure here and the pressure here the same? Yeah, but only up to that line I just dashed off. Right. And then everything beneath it, the pressure's equivalent left to right, increasing as you go down. But everything above this line, well, now it's different because they're just for different fluids. Guys, if I do that, guys, look here, look here. What is this height right here? Guys, what is this? 5 centimeters? You guys see 5 centimeters? Because it's 15 minus this 10. That's where 5 comes from. You guys get that? Guys, focus here. 15 minus 10 is 5. Right. Now, I could say pressure left equals pressure right.
Yeah, I'm doing this together. It's very hard.
The pressure on the left side, I got density of water times gravity field times the depth of water. And on the right side, I got density of oil, which we're solving for, times gravity field times the height of the the height of the oil. Guys, what variable cancels out? Yeah, gravity field. Well, maybe I'll write it in there, but you guys could cancel it out. And so I know I got 1,000 right here, kilogram per cubic meter. Gravity, I can call it 10 meters per second squared, cancels out anyway, whatever. I'm gonna go 5 centimeters here. Oil, 10 meters per second squared, 10 centimeters. Okay, so density oil, 500 kilogram per cubic meter. Alright, that right? Oh, wait, guys, is that right? Guys, did I make a mistake?
Yes.
Because I left centimeters. Guys, I did not convert that to meters first. Is that okay?
Oh.
Is that okay?
Yeah, it says they cancel.
Yeah, the difference cancels out. Yeah, it's okay. Guys, is it generally good practice to put everything in basis SI units? Yeah, so really, maybe I should call this 0.05 meters and call this 0.10 meters. But yeah, at the end of the day, that conversion also cancels. So you still get the same answer. Okay. Everybody have that in their notes?
Yes.
Okay. All right. And so here's a more complex, more fun looking one. All right, so this is all relative to this bottom dashed line, and then the pressure from the atmosphere left to right is almost exactly identical, so you can cancel that out. And then this rho GH naught is same left and right, so that also cancels. So you can simplify the equation. You can do that. Hey, what if guys? Ooh, this one's a little different. Guys, what if you cap the left end so it's no longer open to the atmosphere? Guys, could this pressure right here, guys, look up here. What you guys think about this? Could this purple pressure really be anything? Yeah, you can make it a high pressure, so it's pushing everything up. You can also make it a vacuum if you go the other way. It could be a perfect vacuum. Well, actually, probably not. Well, probably not this exact example, but in general. Okay, so go like that. That cancels out. Okay, you guys good with YouTubes? Good with YouTubes? All right, so guys, we just got 2 concepts left. We got conservation of flow and Bernoulli. And I'll set up some for you guys to solve these. But guys, let's figure out where this comes from. Now, this ultimately leads to an equation that's straight off your equation bank we just looked at. But let's go step by step. Guys, look up here. Guys, focus here. Guys, everybody's look up here. So we've got some water flowing through this pipe system. The diameter of the pipe changes. Because look at this cylinder versus this cylinder. And let's say the same volume. And they travel some distance at the same time, same volume per time. Is that okay? Same volume per time. Now this will work as long as the fluid is not compressible. The water is basically not compressible. The extent to which it's compressible is so tiny, it's negligible. We'll just ignore it. Okay. So we're going to say that the volume per time is the same ratio throughout the entire pipe system. So left side, right side, whatever. Okay. Now let's break this down a bit. Because guys, what is the volume of that cylinder? What is the volume of a cylinder? In terms of this cross-sectional area, guys. In terms of this cross-sectional area and this height of the cylinder.
Pi r squared times height.
Yeah, it could be pi r squared h. Okay, the pi r squared bit is just the cross-sectional area, and then the height can be this x. Okay, yeah, that's true. Yeah, so pi r squared h, that works. I can just do a times h. Okay, is that okay so far? Guys, look up here. Is that okay so far?
Yes.
Okay. Now, can I group together x over t? And guys, what is x over t?
Velocity.
Yeah, there you go. So that can be speed. So okay, so cross-sectional area times speed is conserved throughout the system as long as the fluid is not compressible, and that's how AP would ask it. Okay. Right, guys, good. Right. That's straight off your equation bank. It's the second to last formula on all your equations. Okay.
Yeah.
Now, guys, in college, you might see something compressible, like for example, air. Guys, could air be compressible?
Yes.
Yeah.
That's why.
So, then you'd have to thank you, include the density of the fluids.
No, it's an air compressor.
Yeah. There you go. Like that. Okay, guys, is water considered compressible in this class?
Is there water?
No.
Water
Great.
compressible? No. Water.
Yeah, like guys, if you took a cubic meter of water in this room, it would weigh 1,000 kilograms. If you went down to the bottom of the Pacific Ocean, you got a cubic meter of water, it would basically also weigh 1,000 or have a mass of 1,000 kilograms. Right? It might be like a tiny bit more. Or wait, yeah. Okay. All right, so Bernoulli. All right, here I got a fish swimming around this pipe system. Now, one of the questions that you would have seen on your AP classroom assignment if you did it over the weekend looked a lot like this, and it said, "Does the pressure basically increase or decrease from this point on the left to this point on the right?" Right. So let's come up with a formula and then analyze the formula. Do you guys remember how this formula goes? Guys, go ahead. See if you can write it in your notes. How does the formula for Bernoulli principle go? And yeah, it's on your AP equations. But even better if you can remember it. Did you guys come up with that right there?
Yep.
Equals that right there? Right.
So they look two.
Guys, if you stand back and look at it, does that look really similar to conservation of energy? It basically is conservation of energy, but it's in pressure units instead of energy units. Okay. So, guys, look up here. Guys, I'm telling you how to pass the AP exam. So, what represents what? What does this P1 represent?
Pressure and the load.
Yeah, the pressure this fish feels in that on the left side. Yeah, how much internal pressure does the fish feel from the water?
Water.
All right, so next thing, guys, let's ignore for a moment the fact that the water might be flowing. Is that okay, guys? The more I have to redirect the class, the less content I can teach you guys. Guys, what if the water's not flowing at all? And so you're like in a pool. Guys, if you go from the deep end of the pool to the shallow end of the pool, what happens to the pressure on you? It definitely decreases. Okay. Now, let's switch variables here. I'll even give you guys a different visual. Let's go back to this visual. Let's go from a wide pipe to a skinny pipe, but ignore the height change. This basically has no height change, right? Right. So just looking at that, is the pressure going to increase going from the left side to the right side? Or increase or decrease? Guys, show hands. How many of you guys think going from the left side to the right side, the pressure increases? Who says the pressure decreases? Winner. Well, okay. Yeah, guys, the pressure decreases. Now, let me convince you guys that's true. So, one way you know is, you guys do know the water would speed up, right?
Yeah.
Water would speed up? Okay. Now, because the water speeds up, you can think of it like this last green term is consuming more of the pressure units, which means there's less pressure units to go to P2. Or I can even do a science experiment with you guys. Guys, what if, here's conservation of flow, here's Bernoulli, there. Right? Guys, what if I take this paper and I blow a stream of air over the top? That would be a fast-moving fluid, wouldn't it? Does that push down the paper or does it vacuum up the paper? Vacuums it up. Yeah, I definitely see it being vacuumed up, which would indicate a low pressure, wouldn't it? Low pressure, right? So I think for that reason, go back to Special over here.
Let's.
Whoops. That would further mean the pressure's decreased. So I think for both these reasons, the fact that you're increasing elevation and also you're going to a skinny pipe, for both those reasons, the pressure would decrease and then decrease again. Right? Right, so here I'll come up with something a little different. Okay, let's guys in your notes, draw this in your notes. Let's have a pipe system like this.
Oh, it also stows there.
Okay. Okay, everybody do that in their notes.
I'm running out of
Oh, some pipe here, some pipe diameter. Here. Go like this.
That's extra stuff I have to buy.
I'm still up. Alright, I need to give you guys a height change. So from here, we'll go from the center of the pipe, about like that.
You're gonna end up being more comfortable.
Let's call this height change.
So
How about 25 meters, like a multi-story building. Let's have this initial diameter be 3 meters.
They're in hospitals.
Let's have this final diameter, deep. Well, how about deep final? Be 1 meter.
They're on the older side.
And let's say that the water is flowing up here, plus the initial is 2 meters per second. Let's throw a fish in the mix. And I'll give you guys one more number here. Let's say that the initial pressure, call it P naught, is how about 1,000,000 pascals, which is pretty close to 10 atmospheres. So 1,000,000 pascals. Right. So right now, this fish feels basically 10 atmospheres or 1,000,000 pascals of pressure on it. Okay. No, guys, here. Okay. So as the fish dives deeper, guys, deeper in isolation by itself should make the pressure do what? Should make it increase. But we're also going into a skinny pipe, which means the water speeds up, which should make what happened to the pressure? Decrease. Oh, do you guys see two competing variables going on?
Yes.
Right. Deeper, but also faster. So what happens to the overall pressure? Now, I don't know yet, because I just made up these numbers. But here, I'll give you guys a head start. Guys, go ahead and solve that. Solve that. I want to know what is pressure final. That's your goal. Here's your goal right here. What's the pressure in the skinny pipe down here? So by the time the fish gets down here, how much pressure does that fish feel on?
1 fish, 2 fish, red fish.
So I'll give you guys a head start. Head start. Let's start solving it.
Is it PV squared? PG? No. PV squared. PV. Okay, so A1 is 13.06.
You can assume you're on Earth, so gravity field could be Earth gravity. Alright, so those potentially guys, how do you think about this a little bit? This is actually a multi-part puzzle, and you can't answer that question directly yet, unless you answer some other things first. Like, guys, I never told you how fast the water is flowing through the skinny part of the pipe. Is that solvable? Yeah, but that's not from Bernoulli, that's from what? Conservation of flow. Conservation of flow. Alright, okay. So you need conservation of flow. Yeah, if you know the cross-sectional areas of the pipes. Oh, I didn't give that to you either! No! I didn't give you cross-sectional areas.
No, it's not.
Wait, no, it's solvable. How do you guys think?
I got 10 a lot.
Okay, is there a way you can find cross-sectional areas? Because I did give you the what? Diameters. Ah.
I got the second one. 17. Are you sure? Per second. I think you 18 meters per second. Okay, so then you.
Alright, well, we got 9 minutes of class left, so I'm gonna have to start solving this, but I really want somebody to get me to the answer. Okay, you guys got a good head start? Good head start? Alright, so I'm gonna start with conservation of flow. Say A initial, B initial equals A final, B final. Okay. But this cross-sectional area, I really know is pi over 4 diameter squared. So that can go like that, right? And then the pi over 4 bit just really makes it a circular cross section, but that doesn't matter. So I can cancel out the pi over 4. Right? So, but it is vitally important that you square those diameters. Guys, I've seen AP do this. If they give you pipe diameters, you do have to square those to tell you something about the area. In fact, if it was just d squared, that would just be like a square area. But that'll still work. Let's get you here. Okay. Okay. Now, I'd really like to know at this point how fast is the water going through the skinny pipe. So let's do this. We got 3 meters squared, 2 meters per second equals 1 meter being squared v final.
18.
All right. So what's my v final?
18.
Yeah, 18 meters per second. Okay. Oh, hey, the ratio of the cross-sectional areas is
1 to 2.
1
to 2 to 1.
well, not 9 to 1,
9 to 1.
and the ratio of the speeds ends up being 1 to 9. You see, it's 9 times as fast.
Yeah.
Yeah, is that okay? So that's conservation of flow. Okay. Now we're ready for Bernoulli. You guys ready for Bernoulli?
1 9.
All right, Bernoulli time. So we can answer pressure. Okay, I can only fit so much on the screen here. Okay, so everybody's got that in their notes. Notes. All right, Bernoulli time. Bernoulli. Pressure initial plus rho g h initial plus 1/2 rho v initial squared equals pressure final plus rho g h final plus 1/2 rho v final squared. Okay, straight from your equations. Okay, it's just it's this very last one. That's all I did. I just copied that very last equation. Okay, so I know this number I put it as 1,000,000 pascals. So 1,000,000 pascals. I know density of water is 1,000. It's kilogram per cubic meter.
You knew what you were.
Gravity field, I'll call 10 meter per second squared. And this initial height was up at 25 meters. 25 meters up. Okay. So that plus 1/2. I got 1,000 kilogram per cubic meter here. I got 2 meters per second here. And I don't want to forget to square that. It's really 2 being squared, isn't it? Look at that. On the right side, I really want to know what is the pressure on the fish in the skinny pipe. That's what I'm solving for. Oh, hey! Guys, what's the height at the lowest point?
0.
0. Like if up here I was calling it 25 meters up, this has to be 0. This bit just goes away. That's just 0. Throw that one out. Got 1,000 kilogram per cubic meter on this rope for water.
Yeah, I was at 9 something.
And we just found out from conservation of flow, we're on 18 meters per second. Still don't forget to square that. It's 18 squared. Okay. A little math here. See what we're looking at. So we got 1,000,000 pascals plus 1,000, 10, 25. I'm looking at 250,000 pascals.
I had 30 seconds.
1/2 1,000 2,000 pascals equals pressure final plus so like that. Alright, so
That's just you, bro.
You guys are not. That's like 20 hours. I used to. Do you know the 5x5? No. I used the 5x5. Because they don't want to see.
all right. Guys, overall, did the pressure go up a little bit or down a little bit? Yeah, it did increase a little bit. I wasn't sure setting this up because sometimes the danger is you get like negative pressures. Which guys, can you have a negative pressure and flowing water? Yeah, it turns out you can. Right. I just prefer to tend to not do that. Okay. Yeah. So remember we had these competing effects. Going deeper should make the pressure increase. Going to a skinny pipe should make the pressure Going deeper should make the pressure increase. Going to skinny pipe should make the pressure decrease. Right. And overall, the net effect is the pressure should go up a little bit. Alright.
Every day you were here, I saw the train. No one was there.
Alright, we've got Venturi effect, which is just a variation on Bernoulli. And guys, here's the last slide today. Last slide. So, guys, you're almost certainly going to see some variation of this question. Some tank of water, and you can either take a hose and route it down here, or sometimes you punch a hole in the tank. So let's set up Bernoulli. There's Bernoulli. Now, guys, if this tank of water is open to the atmosphere, which is probably how AP would do it. Okay. Guys, is the atmospheric pressure, guys, last slide. Is the atmosphere pushing down on all this water here almost the same as it's pushing at the end of this hose right here?
Yes.
Yeah. So this atmospheric pressure on the left and this on the right, there might be a tiny bit different, but we'll call that a negligible difference. So we're gonna just cancel that out. It's the same, basically the same pressure. Right? Same atmosphere here as down here. Right? How about guys, what's the height of the water down at the lowest level? 0. So can I get rid of that right there? Goes away. Kind of like the one we just did in your notes. Right? There's one more simplification, which goes like this. Is if this is a big tank of water, approximately how fast is the top of the water level moving right here?
0.
Yeah, 0. Can I call this B right here about 0? Is that okay? So I'll do that too. These are all common simplifications for this question that recurs about every year. Okay? So really that just simplifies to that equals that. Right? Now, if you're asked what is the speed of the water spurting out the end, then what would the answer be? Yeah, no surprise, root 2 pH. Okay. All right, and that's a wrap on today. Oh, here, guys, if you hadn't done it yet, here, remind you guys. Looks like, guys, it looks like about half you guys have done this assignment. So if you haven't done this yet, can you guys finish this tonight so I can debrief tomorrow? Oh, ran out of time on AP. Okay, and then there's that. There's multiple choice questions for practice exam 2. Also do those in the next week, and we'll go over those next week.